forum. Today we have Wasim Khan with us, who is a senior software engineer in our organization, and he would be talking about software bring up journey for SoC. So welcome Wasim on this forum, and I think we can start the presentation now.
Thank you so much. Hello everyone. My name is Wasim. I'm senior software engineer in NXP Semiconductor. I'm with NXP from past 10 years and I have 11 years of experience in embedded software development. I'm working in connectivity and security organization and I have experience in platform bring up team. I'm part of platform team and I have been part of multiple SoC bring up, platform bring up, and I have got chance to work on latest technologies like PCI Express. So I have experience in that as well. So starting with today's agenda is that for a SoC bring up we have various phases like simulation, emulation, interposer, and few more options we use to make sure that the SoC bring up is smooth and like we get the SoC out in first attempt only. So in today's session, our focus would be that what's the software view for these phases? How do we plan software development in these phases? What is the importance of each phase, and what is the goal for each phase from a software perspective? So we would be discussing these phases in details, and we would be discussing that how we can plan our software so that for after each phase we get mature enough so that once the SoC is out, our software works seamlessly on that SoC, and we pass the bringer phase. So. Uh, so today's agenda is that we'll discuss about the NXP, some field where NXP is contributing good, and then we'll follow up with the SoC bring up software journey, which is today's session. We are dividing this session in three parts: pre-silicon phase. So in pre-silicon phase, we have further divided. The phase in simulation, emulation, FPGA, and the interposer, and then we'll talk about the bring up preparation and the fallback option we keep, so that if one option fail, then how we can jump to another option and make sure that the bring up activity goes well. Meanwhile, we debug the issue in parallel, and we'll cover the post silicon phase also, where we have further divided the post silicon phase in system test cycle, performance test. We'll discuss about the hardware and the software issue, and we'll discuss about the errata as well. What are the errata? Okay. So NXP work in various segments. So the target market for the for NXP is like automotive. In automotive field, NXP is doing pretty well, be it automatic car, and be it safety feature in cars. So NXP is market leader in automotive field, and NXP's focus is on innovation and make the things secure, and make sure that we get best out of what uh, um, we get best feature in our car. So in the automotive feature, we are already a market leader, and in industrial and IoT also, NXP is contributing, be it basic the industrial routers like layer based routers, and In mobile also, the NXP is contributing, be it wireless charger, different cables, and other mobile related innovation. So NXP is driving in that field also. In communication and infrastructure, NXP is contributing in 5G, and so we have 5G solutions, and we are basically providing 5G solutions. So NXP presence is there in the 5G and the communication and the infrastructure segment also. Okay, so we'll start with the simulation phase. So simulation is basically a serial software algorithm running on CPU based machine which mimic the hardware logic. So basically we at the very this is the first phase for the software development. So we have when a SoC is planned, right? So we have SoC documents, reference manuals, and ArcDef and other documents we get for the particular SoC. So from using these documents and all, IP register set based IP model is prepared. So for example, if we want to get a model where we need a specific IP, we can get a model of that, and then we can get model where multiple IPs are enabled. So, simulation is basically a software-based software running on the CPU-based machine where we are trying to mimic the hardware logic. And so, the goal for the simulation phase is that the software development can start. So if we are, suppose if we are working on a SoC where some new modules are getting introduced, then to start with with the development, we need something to test our software, at least the functional flow. So on the simulation model, the software development can start. We can test our modules whether the software flow is going fine, it is giving the expected result or not, and we can verify all the features of our say software driver. We can check its functional flow, we can check whether we are getting the desired result and the functionality or not. So basic software enablement can start with the simulation, although there are some limitations that some limitations with the simulation that we cannot do uh, the full-fledged software testing, and some issues cannot be cached in the simulation phase, but at least the functional flow from the functional flow point of view we get enabled in this phase. uh, so the limitation for the simulation phase is that hardware bugs are not identified because as I said that it's basically software based models where we are trying to replicate the hardware and software. So if we are if there is a hardware bug, then it will not be we would not be able to catch that in simulation. And then performance testing can also cannot be done in the simulation, like there are some restrictions in the simulation model. So if we want to do performance testing with some high speed peripherals and real time devices, so simulation model that cannot be done, we have that limitation. So simulation is an important phase. So we test our software for the new IP as well as the legacy IP also. At least the functional flow is tested, and we get to know that our code is working as expected with breakthrough new IP as well as the legacy IPs. So once the simulation phase pass, our basic software is ready for the emulation phase. So we in NXP we use different emulators, like we use Jebu from Synopsys, we use Palladium from Cadence. So in emulation phase, we get enabled for the RTL development. So in emulation phase, the we get we get very close to a real silicon environment. Or the RTL is very close to the real silicon, so it allow us concurrent development of hardware and the software issues. The concurrent development of hardware and software, and it's a reprogrammable logic. So basically we can validate our software in emulation phase, and also we can validate the hardware, whether the hardware is also behaving as expected. If we fix any issue, then we can reprogram, we can come up with a new RTL fixing that issue which we faced, and then we can retest our software, and we can check whether now everything is working as expected or not. So in emulation phase, because it's very so it's almost the real RTL logic which would be burned on the SoC. It helps in catching RTL and software bugs before fabrication. So this is a very important phase, and we basically try with a different emulation model based on our requirement. So basically in the emulation phase, based on our requirement, that what if we want to test a particular, say, boot mode, or if we want to test a particular, say, a few new IPs, and also we can request for that emulation model, and based on the requirement we can test our software. So for example, in this particular slide, I am showing a Jabu PCI transactor. So a use case here can be that if we are working as a PCI endpoint device, and if we want to test the endpoint functionality, then we can use a Jabu PCI transactor working as a root complex, so that it will help us test that our endpoint device is able to communicate with the root complex or not, it is able to do the read and write with the root complex or not, and from the root complex side also, if we are able to access the endpoint's memory bars, that can be achieved in emulation phase. So emulation, one of the disadvantage of emulation is that it's slow as compared to the real SoC. So we used for our because we cover testing of different various IPs. So we use emulation optimization, like we can preload the images in memory, so that it saves time to loading time for the images, and then we apply U-boot optimizations. From U-boot optimization, I mean that it's not required to use a bootloader with all the IPs enabled. We can selectively enable only the required IPs as per our use case. That so suppose if we want to test a PCI Express, then we may not require USB and other peripherals for for testing that particular use case. So we can use U-boot only as per our requirement, and we do apply the optimizations there. So if we compare the configuration we use in the emulation with the full-fledged U-boot configuration, then it's very less. Basically, we keep most of the feature disabled if we want to uh, test a particular IP, and then we use Linux and rootfs optimizations also, because we don't need a full-fledged rootfs. We need a bare minimum rootfs mostly. So we prepare a rootfs with a minimal size, and we only include the must modules in the rootfs. And in the Linux optimization, there are various Linux optimization, like we can enable only the required feature in the Linux, like we discussed for the bootloader. That is one optimization, and then another optimization could be that uh, so from the bootloader we pass device tree information to the Linux. So there at runtime we do the device tree fix-ups. So we can bypass that phase also. We can take the already fixed up device tree, so that we will not go in the device tree fix up, and we would be booting Linux with already fixed up device tree. So such optimizations we do apply to fasten the emulation testing phase, because to save our time and so that we can do more testing with our model. So as we discussed that we plan bring up in different emulation models with different requirements and different phases. We don't enable everything in one go. Rather, we go step by step. For example, if once we get the first emulation model, we can plan to boot it without the DDR. Maybe we can try to boot it from a peb memory which does not require DDR. So and we can check boot to prompt of the bootloaders, and then maybe in the next phase we can try with a model which has DDR enabled, and with this model we'll get to know whether the DDR is working as expected or not. Once that phase is passed, then we can plan for a say U-boot or U-boot with a minimum U-boot and Linux boot with a minimum root FS, and then we can try enabling the new IPs in the U-boot. Once we make sure that the legacy IPs are working fine and we are not facing any issue, model is working as expected, then maybe we can switch to testing the new IPs. We can enable their support and then we can test them. If we find any issue, we can fix that issue, be it a hardware issue, RTL issue, or a software issue. So, and then we can retest the thing to make sure that the issue has been fixed. So we can enable new IPs, and then once these phases are passed, then we can basically go with a relatively full-fledged, a bigger Linux with the legacy IP enabled, and with the Linux with new IP enabled. And once we make sure that the legacy IP as well as the new IP are working fine, we are getting the expected results, then we go for the tape out. So that we basically confirm that our software development and the RTL is working as expected, and the software is also working as expected. So we can go for a tape out after that, after verifying all these phases on the emulation model. There are many advantage of emulation models. In fact, I would say that it's the most important phase for a SoC bring up cycle. So, because emulation provides simultaneous development of RTL RTL for software, development of RTL and the software, so we save a lot of time. So as we discussed that the we start with a particular model and then we test our software. If we find any issue, be it the RTL issue or the software issue, then we respin. We basically try to test it with a new model with that issue fixed. So we get a because we are the software and the hardware are working simultaneously. We get a lot of we save a lot of time there. So we call it time to TTM, time to market gain. So in this figure you can see that traditionally if the software development was starting from here and we end up here, So it used to be a linear process, but now with the emulation phase, if the software development can start at this phase itself, where the RTL itself is getting matured, then we save a lot of time to hit the market, and we get faster TTM there. And with emulation, in emulation we can catch and fix the software and the design issue in the development phase, and we can fix them. We can identify the potential errata, and either provide their workaround or fix them in the RTL itself. So here errata, I want to cover a bit on errata, that like for software we have bug. So errata is a technical way to say a hardware bug. So if we have a hardware bug, we call it, say, errata. So in emulation phase, our goal is that we verify the IP thoroughly, and if we catch any hardware bug, we can either fix that hardware bug, or we can issue a errata with a workaround, and we cover all the part of that IP. And the goal of the emulation is that we get the first time right silicon. We don't want to respin the SoC. So we make sure that we do thorough testing in the emulation. We do verify our software. We do verify the software with the RTL design, to make sure that all the IPs and all the functional issues are fixed, and uh, we have tested all the features of the IPs. But there are some limitations with the emulation also. Bugs with which may come with the external real-time devices, they are very difficult to catch in the emulation phase. So that is a limitation in the emulation phase, that with external real-time devices, it's not like we cannot guarantee that it will be catched in emulation phase, because the real-time devices behaves differently. Sometimes the situations, traffic situations occurs, which cannot be mimicked in emulation environment. So these bugs are difficult to catch in emulation phase. So that is a major limitation in the emulation phase. Uh, okay, and for that, to test the real-time devices, we use FPGAs. So the advantage of using FPGA is that a specific hardware IP can be tested in a nearly real-world environment. So the limitation we faced with the emulation phase, right? That the bugs with the real-time devices are difficult to catch. So that can be to target that in these issues, we can use FPGAs. There we can do testing with the real-time devices, and we can make sure that the SoC and the platform is working as expected with the external real-time devices also. For example, in this block diagram, I have shown a FPGA. There we have a programmable logic which we can update, and here I am showing that a PCI link is there between with the external device. So we can test our PCI IP logic with the various external devices, like Ethernet cards, and say networking devices, PCI based networking devices. And once we make sure that all the external devices are working fine, we can say that the IP logic is working fine with the external devices, and we can move to the next phase after that. So FPGA using FPGAs are recommended for breakthrough new IPs. So it is recommended that if we are trying to enable some new IP, then we do get it verified with the FPGA, where we can test it with the several external devices also. And as like emulation, the FPGA logic is also programmable. So if we find any issue, then we can fix that issue in the RTL, or if it's a software bug, then maybe in the software, and then we can check validate on the FPGA again whether the issue has been fixed or not. Okay, so moving on. We we till now we have talked about enabling various IPs in simulation, testing various IP in simulation and emulation phase from SoC perspective. Now we have interposer also. So interposers are boards which are interposers are platforms where we can verify the board functionality. The board validations are done using interposer, and we can validate different peripherals on the board. For example, on the screen I am showing LX2160 QDS interposer, where we use a different SoC on this board. So basically in interposer we use the while the SoC is not ready yet. If we want to verify or the validate board peripherals, we can use interposer. So in this particular interposer, we can use a different SoC and verify that the legacy IP, legacy peripherals are working fine or not. There is a limitation that we cannot validate new peripherals or IPs because we are using a SoC, old SoC to test the board peripherals. So for this board, we have provision to configure it that in which mode it need to work. So we have Swiss settings on the board. So we have Swiss settings on the board to configure it in to configure it as a interposer, that it will work with which SoC. For example, if we want to test a LS2080 silicon, then we can change the Swiss setting to make it work with LS2081, and we can verify the various board peripherals. And then changing the Swiss setting, we can make it work with the LX2160 SoC also, so that once the SoC is once the SoC is available, we can replace the SoC on this interposer board, and then we can use it as a LX2 silicon also. So main use of interposer is to validate the board peripherals. Okay, so we have discussed about the simulation emulations, FPGA interposer in the pre-silicon phase, and then once that is ready, then we plan for the bring up. So during the SoC bring up, we plan with the images with minimal features, that we will try to disable all the features which are not required for a basic boot, and then we would try to use that images initially. Then we create images with different boot source also. So on our platforms we have different boot source like FlexPy boot, or the say USB boot or MMC boot. So we prepare images with different boot source, so that if we get issue with one boot source, we can move to another boot source, and meanwhile in parallel we can fix the issue with the earlier boot source. And then we try to we prepare images with different boot modes also, like we want to do a ddr boot or we want to do a pep boot. So this is very much required, because if we are working on a new SoC, and if say the DDR controller, if the DDR controller is new, or if there are significant changes in that area, then we may face issue during bring up. So we need to prepare images with different boot mode, so that we can at least get enabled, the team can work on the legacy and the new IP. And meanwhile, if we face any issue with a particular component boot mode, that can be fixed in parallel. And then we go with the larger image, where we enable various IP blocks in different phases. Say we can enable say networking blocks, and we can say enable PCI blocks. So we do verify specific IP feature related testing, and we prepare images enabling these IP blocks. And then once all these are done, we can go with a full-fledged image where all possible IP blocks are enabled, and that would be our final goal, to boot with these images where all the IPs are enabled and working. So the motive for all these phases is that we do a day one bring up with SMP Linux boot. So our goal is that our software was ready in the pre-silicon phase, and then during the bring up phase, we target a day one bring up for Linux boot. And for that, we make sure that if we get stuck at some point, then we can fix that. Meanwhile, we can move forward with another boot source or boot mode, or say disabling that IP. So during the bring up, we use flash emulators also. This is one of the emulator, daddyprog emulator, I'm showing in the on the screen. So emulator are very much required if we are anticipating any flash related issue. So our platforms do support boot from emulator. For example, using changing the switch setting, we can decide whether we want to do a normal boot from device 0, or we want to boot from the images which are flashed on the emulator. We can burn the images on the emulator, and then we connect this emulator on the platform, and we can boot with images stored in the emulator. So it's a fallback option for flash related issue during bring up. And it's also an option to use to update the images. Suppose to update the images, we need networking to be working. If the networking is not working, and if we want to say update the images on the platform, we can use emulators in that case also. So we can update the images using emulator. So it's a fallback option to update firmwares also, if the networking or the external flash programmer is not available. So we'll after that we move to the post silicon testing. So there, based on the new features and the use case, the test requirement is uh, prepared. So basically, based on the requirement and the use case, test cases are analyzed and they are written. And then we once we have test cases ready, then we can automate them, and we can start with the test code development. And once the test cases are ready, we can go with either manual or the automated testing for various features. And then the individual bugs and the issues are reported in these IPs, or on these modules. Then it will get fixed from the software, and then maybe retest that same feature. And then after the individual features are tested, then the we can go for the integration testing, where all the system is tested as a whole, and the regression testing is also done to make sure that the IPs and the modules which were working fine earlier, they are still working fine as expected. So we can further divide this post-silicon testing into different phases. So, for example, we can divide in the functional testing, and then the performance testing, stress testing, and the use case specific testing. So we have the desired hardware platform where we are booting with a particular bootloader. So a bootloader can be a U-boot, UFI, or any other bootloader, which is booting the operating system like Linux, and we have a basic root file system support available there. For the functional testing, we can categorize as platform functional testing of platform support modules like GIC interrupt controller, then SMMU from ARM, and the platform devices testing like DMA, Watchdog, IFC, Flex Timer, and then the basic peripheral testing like UART, I2C, RTC devices, then the Watchdog devices, GPIO devices. So we can test these devices, and then maybe functional testing with external devices like PCI Express, USB, SATA, the testing of virtualization modules, networking modules, security modules. So in this category, we can basically do functional testing of various modules. After that, we can do performance testing of modules like the PCIe, the DDR, cache. So they require performance testing. They make sure that we need to make sure that we are getting the desired performance out of these modules. So they can be covered in performance testing phase. And then we need to do stress testing also. Sometime we may get issue with stress testing of a particular IP. So we do stress testing with the different modules like PCI Express. Using PCI Express, we verify various networking cards, various Ethernet cards. We verify, we do stress test for say multiple days and weeks. We do stress testing of DDR, DMA, networking modules. So these testing can be included in stress test segment. And then maybe we can move to use case specific test. So this is a very important test phase. There we based on the customer specific use case, we plan testing that for particular use case, what are the surrounding area and what all need to be covered. And then we use case specific testing for flex builder also. So flex builder is tool to generate images for NXP LSTK releases. So we plan for testing for that use case also. So we using this phase, we cover the post silicon testing there. So the goal of this phase is that we should be able to cover all the modules to a very good extent, and make sure that all the feature, performance, stress test with these modules are working fine. And then in the post silicon testing, if we are facing any issue, then that issue would be reported. Now that issue can be either a software bug, or it can be a hardware issue as well. So as we discussed earlier, that if it is a hardware bug, then we issue a errata for that. If errata is possible for that issue, So our motive is to catch the hardware issue in the emulation phase itself, and to make sure that that all the hardware issues are validated in emulation phase, and we issue the, either we fix the hardware issue in the emulation phase, or we issue the errata with the workaround in emulation phase also. But here in there is also a rare possibility that in post silicon also we may get some hardware related issue which are coming in real case testing. So we call these issues as errata, and we try to provide a workaround for that. And our goal is that the minimum possibility of severe errata. Our goal is that we do catch the issue, the errata and the issue in the emulation phase, and we don't need to issue any severe errata. So to summarize that, what we have discussed is that we have discussed the pre-silicon phase, where we start with the simulation, and this phase enables us for the software to verify the software functional flow, and get the software ready for the next phase, that is emulation. So in the emulation, the software and the hardware development is done in parallel. Our goal is that our hardware, RTL logic, and the software is validated to maximum extent. We should be able, we try to find all the possible issues in this phase, and if there are any hardware related issue, then we either try to fix them or issue a workaround there, and then validate the peripherals using interposer boards. Means using older silicon, we can validate the peripherals on the upcoming board. So we call that interposer. So in the pre-silicon phase, we cover these phases, and then we move to the bring up preparation and the fallback option. So we try to cover different, we try to create different images for different use cases, different boot modes, and our goal here is that we should do a day one bring up. We make sure that the SMP Linux is booting on day one itself, and then in the post silicon phase, we do test, we run the test cycle. We try to do as much testing as possible to cover all the modules, and then if any, we do the performance related testing also, and we make sure that we are getting the desired performance coverage in this phase. And if any issue is found in this phase, then that is reported. So this is the overall picture of the SoC bringer from a software perspective, that in the pre-silicon phase, what are how much is the software developed, what are the goals of the pre-silicon phase, what are the expectation and goal for the bring up phase, and what is the expectation and the expectation from the post-silicon phase. From a software perspective, we plan these phases so that our SoC so that we get the correct SoC in first attempt itself, and we can go ahead with that SoC version. So with that, I would like to conclude my session on this topic. If there are any question, maybe we can go ahead with that.